Today, I say yes, Samar.
And myself Kavya Shah.
We are presenting case study on an Intel Pentium Pro 56. So this process launched in November 1995.
And it was a Intel architecture 32-bit, and it was built on CISC architecture, and it was designed for high performance servers and workstation. It was not for the usual home computers.
The core idea behind launching this process to convert sys instructions into RISC-like instructions, that is, into simpler forms.
And then comes the key features. There were three mainly: out of order, register renaming, and speculative execution. So, first comes out of order execution. The operations are not executed in the original order, rather, they are sent to a buffer where the data, as soon as it gets ready, it is executed.
And the second thing is register renaming. It has 40 internal hidden registers, so it helps them to use the same register at the same time.
And then the third feature, speculative execution. The CPU guess which branch will go and which will start. So if it's right, it would execute, but if it's wrong, then it would start from the base again.
Let's move to the third part, data path and pipelining. So it has a 12-stage pipeline and which allows it for a higher clock rate.
And then the second was superscaler. So it was a three-way superscaler. So we can execute three 32-bit instruction in a single clock cycle.
The third thing is branch prediction. So with branch target buffer, it has a highly advanced dynamic branch prediction unit.
Comes the four execution units that run in parallel: two integer ALUs, one complex integer unit, and one floating point unit, and two load and store units for memory access.
So let's move to the fourth part, that is memory hierarchy. The first one is the L1 cache. It uses two L1 caches, instruction and data cache. And the killer feature is the L2 cache, adding a multi-chip module into the L2 cache. That's the revolutionary feature P6 introduces.
And these both caches were connected by a special private bus, the backside bus. The benefit of this was that it made the L2 cache access 3 to 4 times faster than any competitor brand, and which gave it a massive performance boost.
So let's move to the fifth part, specialized features and parallels.
The first is instruction level parallelism. The entire point was to achieve three main features, as we talked about: the superscalar, the 32-bit design, the out of order execution, and the speculative execution. The second feature is symmetric multiprocessing. So it was built from the ground up for the servers. So it had advanced programmable interrupt controller, and it made it two-way and four-way and even eight-way multiprocessor system.
So the third is physical address extension, that is PA. It was the first 32-bit CPU to introduce PA that allows a 32-bit OS to use a 32-bit physical address. So let's move to the last point, the historical significance and impact.
So the P6 microarchitecture was arguably the most important design in Intel's history, because it had core concept: the 6 to RISC micro operations, the out of order execution, and the buffer which was used, and so it formed a successful foundation for the Intel CPU.
So there is a comparison. So you can see that ISO code, that is CISC, previously the CISC is used only. Now we have the CISC to RISC translation. The pipeline is changed to 5 stages to 12 stages. It was a flop for home users because it was actually so slower at 16-bit, but was dominated the server and workstation market and completely solidifying Intel's control of that segment. So that's the end of our case study. Let's now move to the two assembly codes that are assigned. So this is our first program, the factorial one. So let me explain you this code first. So this first section data is our starting point where we introduce the number which we have to calculate the factorial of. And then this is where our program starts and stores the numbers in the register. Start will set the counter and the result in the register. Now this fact loop will do the multiplication and add to the numbers as well and decrease the counter as well. This print loop will just call the print number function, which is this, which will print the numbers of which will print the number in the console. This exit function will exit the program successfully with the exit code 0, that is the success. The convert loop is there to just convert the string to the number. The to print will successfully print the string we have just made. So let me now just run this one. So from these two lines, we have successfully converted our assembly language code to the machine code. Now when I run the file factorial, so you can see here it is printing the factorial of 8.
So now we move on to the second program where we print the first 10 number of the Fibonacci sequence to the console. So this is our expected output. Then we start from the section where the 10 digit is max for the 32-bit number, and we add 1 for the new line, and we give the buffer 11 value. Then we move on from the start. Here we store the value 0 and 1 to the EX register and EBX register, and then we assign 10 value to the ESI register, which will be used for the loop counter. Then comes the Fibonacci loop part where we compare the ESI value. If it reaches 0, we exit the program, and if it doesn't, then the rest of the code execute where we will print the number. We will perform the calculations for the Fibonacci sequence. Uh, then we will move on to the loop part where the string will be converted to the number, as in the start we took string in place of numbers. And after that we will print the Fibonacci sequence, and once the counter reaches 0, we will exit the program. So now with the first two lines we convert the assembly code to machine language, and now we will run the program. And as the expected output was, we print the first 10 Fibonacci sequence.